Hi everyone, I'm Phil McMinn from the University of Sheffield, which is in the UK. I often get asked this a lot at conferences, so I thought I'd make it my first slide just to clear up exactly where Sheffield is in the UK. It's basically in the middle of England. The nearest city you probably recognise is Manchester, probably because of Manchester United and Manchester City. But yeah, we're about 50 miles away from Manchester. It's about a 2-hour train journey from London, so they're not too far away from one another. It's a fantastic place to live and work. These pictures are a bit pixelated, but this is basically a picture of the city. It's built on 7 hills, so likenesses have been made to Rome in that regard. But it's also next to a big national park called the Peak District, which exists between Sheffield and Manchester. So to get from one city to the other, you have to traverse this national park, and it's very scenic. You can get out from Sheffield to this scenic park in about a 20-minute car journey at most. So it's great to combine like a busy city life with nice countryside. So it's a great place to live. We're a big computer science department. We have groups in software testing, verification, security, machine learning. Every 5 years, the UK conducts this thing called the Research Excellence Framework. And in the last one that was conducted in 2014, we were 5th out of 89 computer science departments. So that's just my little boast for my institution out of the way. Also, this is a bit sneaky, but I just wanted to advertise this. If anyone who's interested, to pass the message on. We're an expanding department. We're currently hiring in the areas of verification, testing and cybersecurity at all levels, from full professor down to assistant professor. So like I say, if you know anyone who's interested, please pass the word on, because we want to hire some great people. I'm a reader. I'm an associate professor at Sheffield. My main research area has been search-based testing. I am more broadly interested in software engineering, particularly testing, but this is the area that I guess I'm most well known for, and this is where I concentrate most of my efforts. I'm co-program chair for SSBSE next year, so I guess it's another kind of advert subliminally this time, just to advertise that event and to get your papers in. The call for papers will be distributed very soon.
You want to explain to
sure.
Our guest what is SSBSE?
So SSBSE is...
okay.
Yeah, okay. Do you already know about it? Symposium Search-Based Software Engineering, and it runs every year.
Just to be sure.
And it's not just limited to testing, although there are a lot of testing papers that are submitted there. The main sort of theme throughout this talk, I'm going to sort of cover lots of different bits of work I've done. And some of the details might be a bit shallow, but I'm going to give the references so you can follow up in more detail if they interest you. But it's about this stochastic optimization technique called the alternating variable method. But local search in general is based around making small local changes to some candidate solution, and there are benefits to doing this for certain types of problems. One of the disadvantages of a local search technique is it can get stuck because it's very sensitive to the shape of the underlying so-called fitness landscape. The kind of curve that the fitness function will plot. But in that case, it can be restarted, and that's also been shown to help this technique produce good results. It's been found to be faster than global search methods for certain types of problems as well, and I'm going to go into some of those problems for which it's worked well and which we've got good results. This is basically local search visually. This is something that we call the fitness function landscape. It's basically a plot of the fitness function that's been developed for a problem. And here we've just got a one-dimensional problem. These are all the potential solutions to the problem that are plotted along this kind of abstract horizontal axis. But basically how it works is local search will make small changes to the candidate solution to try and develop better solutions that have better objective values. And it will sometimes called hill climbing because it will climb the curve of the fitness landscape and hopefully reach the global optimum, which in this particular graph is the green zone. As I was saying, one of the drawbacks of local search is that we can get stuck in local optima. So if we were to start with a solution down here, for example, we'll climb this particular hill, which is suboptimal globally. And this would be a scenario in which we might want to restart the search and choose another random point in this landscape in order to climb some hill that will lead to a better overall solution. And one particular search method that's been of strong interest to search-based software engineering researchers for quite a few years now is this technique called the alternating variable method, which was first used for test data generation in the 90s. But it's been used in other domains as well, such as workload allocation, so allocating software requirements to different programmers, and in software product lines as well, and a few other problems that I'm going to talk about today. But it's a fast and been found to be a particularly effective search method in search-based software engineering. And the crux of the AVM is basically to reduce your search problem to a vector of variables. And once you've got this problem representation, you can start to use the AVM operators on it. The vector is evaluated according to a fitness function as usual, so you have to have a fitness function in order to get this to work. But what the AVM will do is it will start moving through the vector of variable values and start to make so-called moves on them. And the first thing that we'll try to do is make exploratory moves. So basically what this means is it will make small tweaks to the variable value, it will increment the value and it will decrement the value, and then see if it can establish a positive or negative direction in the fitness landscape. So after making one of these small changes, can we establish which direction to move that variable in the future so that the fitness values will increase further. So it's kind of like a little sensitivity test. We push it one way, we push it the other way. Does the fitness improve? And if it does, then we can start to make larger moves in the same direction. So suppose for x1 here, we make a small increment to x1, and we find that improves the fitness value. What the AVM would start to do then is start to make these bigger jumps on that particular value. So it starts to do something called pattern moves, and these pattern moves get larger and larger and larger, so long as fitness is being improved. As long as the fitness has been improved, these pattern moves continue. As soon as fitness stops being improved, then we go back to the exploration mode again. So it starts to try and re-establish a new direction for this variable and then try to make further pattern moves. And if it can't establish a new direction, it'll move on to the next variable and continue to do exploratory and pattern moves through the vector, considering all the variables in turn, and then starting back at the original variable in the vector once it's done an entire sweep. So this is visually what's going on back with our one-dimensional fitness landscape. But suppose we start with a randomly produced vector initially, the green star here. These two moves here correspond to the exploratory moves, and we can see that increasing the variable value in this instance has a positive impact because we now have an improved fitness value. If we decrement the value, we end up at this position here denoted by the red star, and fitness has decreased. So we've established through these exploratory moves, through this kind of sensitivity analysis, that increasing the value of this variable is a good thing to do. And then these pattern moves start. First of all, it's twice the size of the exploratory move, and then it's twice the size again. So we keep making these big jumps. And we have improved fitness values until we hit this particular red star that I'm highlighting here, where fitness has got worse. So you've got a situation where fitness was improved and then became worse. We know that somewhere in this region we have an optimum. And then the next stage of the algorithm is trying to identify exactly where within these 2 points the algorithm, the optimum is. And there are different ways to do this. So in the original alternating variable method that Coral proposed, he just proposed basically to continue the exploratory and iterated pattern search until you eventually hit on the local optimum. Some recent work that we did found that this was very inefficient in certain circumstances. We invented two new methods to locate the optimum. One is a geometric search, where you simply just do a binary search once the optimum is bounded within 2 points, and another method called lattice search, where you start to build out from the last point using Fibonacci numbers to locate the optimum once it's been bounded. And we were able to prove, well, my colleagues were able to prove at least, I was just involved on the practical side of this, that these two techniques are provably faster when the landscape is unimodal, which is surprisingly often for test data generation. We built this nice little framework that implements all of these different search methods. With this framework, you can build up your problem representations. We've implemented lots of basic data types that you can build up a problem representation from. So the original AVM was designed to work with integer numbers, so of course we have those. We've extended it so that you can use fixed point numbers with the AVM, and also you can have variable length strings as well. So we have a way of modelling subvectors within the overall vector that can be of variable length. And we achieve that through having different moves that we built into the AVM algorithm that can reduce and expand these subvectors to kind of model strings. And we implement these different strategies for finding the optimum that I've just discussed, like geometric search and lattice search. And this is available on GitHub at these particular URLs, and there's a supporting paper that was published at SSBSE. And it comes with a number of examples as well to get started. One of our motivations for producing this tool was that we noticed there were lots of different ways actually in which authors were implementing the AVM. And sometimes in our own work with students, we noticed that they were reinventing the wheel a lot and introducing certain bugs into it. So one of the motivations for releasing this tool was to have a standardised way for people to use the AVM method and get started really quickly with some sample problems. So the AVM is classically used for structural test data generation, and I guess lots of people in this room will know how this works, but for some of the people that are new to this area, maybe they don't. But I just want to cover this quickly, but essentially in structural test data generation you've got your control flow graph where the diamonds represent the different decisions in the program and the blocks represent the different statements. And then basically what you do when applying the AVM is to map the input vector of the particular function you're testing to one of these AVM vectors, and that can result in a very large search space. And what you're trying to do is solve the different constraints that correspond to the if statements in order to find test data that will execute them in the different ways that you want them to be executed. So here we've mapped our function with the inputs A, B and C to this vector with 3 and more variable values in it. And supposing this branch here has the constraint if A is equal to B, then we can map these to different fitness functions that when you minimise them, the branch will be executed. And the deeper the nested the target, the more constraints that will need to be satisfied, and we basically combine all these different fitness functions to produce an overall fitness function, and when that is minimised, basically you'll have found an input vector that will traverse all of these different decisions and will execute the target statement. So traditionally in search-based test data generation, evolutionary or genetic algorithms are preferred. In some work that I've done, I've actually found that local search often outperforms global search at generating test data values. But that actually a combination of the two is the best of both worlds solution. So we've got some work where we did this with some C programs, and we also implemented the AVM into the Evo Suite tool as well, with some good results. So you've got your typical evolutionary algorithm loop, which has been covered by others today. But essentially, incorporating the AVM in such an algorithm to produce a so-called mimetic algorithm just involves part of this loop being devoted to trying to improve each individual of the population with an AVM search to try and get the maximum fitness possible by basically moving that individual to the top of its local optimum. And in our study with Evo Suite and experiments with about 12,000 classes, we found there were some large increases in coverage that were possible by incorporating the AVM into the search, as much as 53% in one particular class. And we found that it was able to improve Evo Suite's results, particularly with classes that had methods with numerical and string inputs. One of the recent problems I've been working on is database testing, and in particular schema testing. Despite the rise of NoSQL database systems, relational database management systems are still in wide use in a wide variety of applications. And two common vendors for DBMSs include Postgres and SQLite, which you may have heard of. And this particular problem considers schema testing, where in particular we're interested in ensuring that the integrity constraints of the schema are being properly specified. Now, a schema of a relational database system consists of a number of tables, each of which will have rows and columns in. But typically the schema will also involve the definition of integrity constraints like primary keys and unique values, unique columns, and check constraints. And these are things that need to be tested on the basis that they are defending the database from taking illegal or values that basically shouldn't be accepted into the database. So they're basically defending the database and preserving its integrity with these constraints. And our method basically involves generating insert SQL statements that form the basis of a test suite. And we have certain expectations on those insert statements that they should be accepted or rejected in certain scenarios. And testing the schema in this way may lead to us discovering that a table may have a missing primary key, for example, or that a unique constraint has been incorrectly specified. Or it could be that we've got a check constraint which has an arbitrary condition attached to it that may be incorrectly specified. And the test may reveal that the insert statements with generated data in are accepted or rejected when they shouldn't be, and this may lead to a fault being detected within the schema. And this is an important problem because various commentators have reported big monetary losses through incorrectly specified schemas and the resulting poor data quality. And various industrial commentators talk about how it's important to test the schema, but there's no current automated method for doing this. And this is what we've produced with our tool Schema Analyst, which I'll put the URL for later. But essentially you could have a scenario here where you've got a table that's representing a number of users in your system. So we record their names and their login credentials. But it could be that in this particular table, the schema designer has neglected to say that the username should be unique. So each user should have a unique username. And our system can go away and generate insert statements with generated test data that try to cover different aspects of the schema, such that it will generate two insert statements here and find that the second insert statement is passing when actually the user would expect that it wasn't passing because the username has been duplicated. So this will then lead the tester to realise that actually there's some missing constraints in this particular schema. Another good reason for testing the database schema is due to different interpretations of the SQL standard. So one common scenario when employing databases in an application is to use some kind of lightweight DBMS like SQLite when the software is being developed, but then using a robust enterprise DBMS like Postgres when it comes to deploying the system. And actually, it's quite common for different DBMSs to interpret the SQL standard differently, and this can lead to bugs when the software is being deployed. So famously, SQLite allows null values in its primary keys, which most other DBMSs do not. And another common one is Microsoft SQL Server, which basically with its unique constraint considers null to be a unique value so that you can't submit another null value into that particular column if that column's been marked with a unique constraint. Whereas most of the DBMSs will allow as many nulls in that column as you'd want, because null is considered to be an unknown value, so therefore it's unknown whether the null value is unique or not. So there are these subtle differences between DBMSs and their interpretation of the SQL standard, which means that it's important to test the schema, because it could be that your application is behaving differently in deployment as opposed to how it was developed. And the AVM can be used here to generate test data to go in these insert statements according to different coverage criteria that we've devised. And these coverage criteria include exercising each integrity constraint as true and false, ensuring all the columns are being exercised with null values and things of this nature. And the values that go into the insert statements we map to an AVM vector. The AVM then solves the problem through a fitness function that's mapped to the integrity, the coverage criterion, and then our system will track whether the insert statements are accepted by the DBMS or rejected. And then, as is commonly the case with automated test data generation, the human would then have to analyse the results of those tests to see if they're as expected or not. So we have this tool, Schema Analyst, which is available at this URL and a couple of supporting publications. And it basically takes a schema in its SQL format. It'll generate an abstract representation of it so that it's cross DBMS. Currently, Postgres, SQLite, and HyperSQL are supported by our tool. And we can add more DBMSs into our tool on the basis of having this abstract representation. And our tool will generate test suites for these schemas. We've also got mutation analysis built into it as well, so that we can insert faults into these schemas automatically and see what the quality is of the tests that we are generating. And in our work, we find that AVM is capable of generating high coverage test suites, and that they're capable of killing high numbers of mutants as well, as high as getting perfect mutation scores and no lower than 75% of mutants being killed. So at this point, I just wanted to take a brief aside. This part of the talk isn't specifically right. Hi.
What do the mutants look like? What type of fault do they try to eliminate?
Mm-hmm. So they mutate the schema. So basically, if you have an integrity constraint of primary key that might have one column, then it might change it so that it's now got two columns. It might remove an integrity constraint altogether. If it's a check constraint that has, something like x is greater than y, it might do like a traditional type of program mutation mutant where it's like x is greater than or equal to y and things of that nature. So these kind of small changes. So this particular part of the talk isn't related to the AVM as such, but it's an important problem because, as I said, when we generate these test cases, the inputs are generated and we can see what outputs are produced to those inputs, but it's still the case that a human would need to look at the test cases and the results and see if the results were as expected for the inputs. And machine-generated test data tends to be aimed at just coverage only. The values that are produced tend not to be so readable or understandable by humans, which in turn makes this job of the human acting as the oracle, essentially, difficult to undertake. So a search-based tool or random testing tool might produce integer values such as these here, when a simple 0 or 1 would do, and that would be something that's simple and abstract enough for a human to see immediately what's going on with that test case, what the test scenario is that it's trying to represent. And for string values in particular, we can get unwieldy characters, sequences that are generated that look quite arbitrary when actually we'd want something that looks familiar and readable to a human, such as a real email address like my own. So a couple of techniques that I've been working on to try and address this problem is to produce, specifically tackling the problem of strings and readable strings. One particular approach we've taken is to incorporate something called a language model as on a secondary objective into the search-based testing approach. So the first objective is to obtain coverage, but then once coverage is obtained, the search then goes away and tries to optimize readability, where readability is a metric of something called a language model. And the language model will give scores based on how readable it judges the strings to be, and it assesses this based on the bigrams of the characters that appear in the string. So by taking a suitably large corpus, we can basically estimate the probability of certain letters occurring together in a particular language. So in English, for example, we'd expect QU to have a very high probability because those two characters tend to come together in English, whereas other sequences like U5 or 5S would have very low probabilities because they don't occur in words in the English language. So by having these bigram properties, we can basically come up with a fitness function that can assess how likely the particular string is to have come from a piece of text in English. So the word testing, for example, has a language model score of 0.176, whereas this random arbitrary string here that we've just come up with has a very comparatively low language model score. And we can optimize now this language model score in order to generate sequences of characters that have readable aspects to them, readable elements. And this is how we incorporate it into the search-based technique. We've got the usual fitness function that looks at the constraints appearing in the if constraints. And then as the secondary objective, we have the language model score that kicks in when the particular target has been covered. So this function here is basically taking a string that's a variable name with underscores and converting it to something, a variable name that's camel cased. So to execute this particular branch, branch 6 as true, it's looking for a string that has one particular underscore in it so that it can do this conversion into camel casing. So a string that might be generated randomly by the search-based tool might be to have the underscore character in it, but then basically a bunch of junk characters either side. Whereas our technique can produce strings that have sort of readable, more readable to the human character subsequences that make the presence of that underscore easier to see and identify, and for the human oracle in that case to see what that test case is doing and be able to correctly say that the outputs match the inputs. So we did a human study to evaluate this, to analyse the ability of humans to basically look at the test cases and basically say, is this output correct for this input? And what we found with the language model was that not only did it increase the time that humans were able to make these judgments, they're basically able to look at test suites with test data generated by the language model and process those faster. They're also more accurate as well. So when acting as the oracle for test suites, humans may make mistakes, but with the readable test data, we found that they were liable to make fewer mistakes, which were both positive results. Other things we've looked at are looking at the names of variable values used to try and determine what type of data they represent. So looking at the actual variable names themselves, or the function or method names, or the class names, and so on and so forth, and using these as kind of indicators as to what string value should go in there. We did some natural language processing on these values to basically generate web queries, which could be used to look up web pages that may contain particular examples. So if you were to take one of these identifiers and to do standard natural language processing on them to remove stop words and to split them into words and so on and so forth, you can find out basically what the keywords are and put them into a search engine, which will return a bunch of web pages that may actually contain examples of the strings that we're kind of looking for. So if you search for email address in Bing, you'll get one of the search results will be the web page, basically detailing what an email address is. And as part of that web page, there's an example, lewis@example.net, which is an example of a real email address, and we can extract that and use it in the test generation process. And when we applied this technique to a bunch of programs that were validating different string types, we were able to execute certain key paths through the program that were responsible for identifying certain valid values and improving the code coverage in those cases. So just moving away from testing, I just wanted to cover some more recent work we've done using the AVM for fixing website layouts, which is a new kind of direction for using local search. And there are different ways in which website layouts can be faulty. One of which is cross-browser issues, where basically the developer develops their website and they test it in one particular browser. So here, Internet Explorer, they ensure that everything looks correct. They've got the various tabs with the links and the text in them. But then as soon as the web page is rendered in another browser, they find that things have moved around and things don't look quite the same. A common problem. And the reason that this occurs is because of inconsistencies in the different ways that the different browsers have interpreted the HTML and CSS specification. So whereas we have a perfectly functional web page here where the users can see the different links and they know what they're clicking on, here the text has become obscured. And this is a cross-browser issue that will cause a problem for anyone who's viewing the page in Firefox. Another type of failure is the responsive layout failure. So nowadays websites tend to employ responsive web design, and this is where web pages will adapt the layout of their content for different types of devices. So instead of just having a desktop website, this website will readjust its content so that it flows neatly within a laptop or a tablet or a mobile phone device. And this is a whole area that can lead to a whole bunch of layout failures to do with the logic that's responsible for adapting the flow of the website so that it will fit the new space for which the HTML elements are supposed to be rendered in. So this is an example of a responsive layout failure where two rules in the CSS have been switched on at the same time for a particular viewport width when they shouldn't have been, and some of the text is obscured. Here, the web page has started to become contracted along the x-axis as it's trying to fit into one of these smaller devices. And what's happened is the HTML elements have started to overlap with one another. So the go button for the first input box is being obscured behind some of the other web elements. A third type of common layout failure is to do with international presentation. They're called international presentation failures, and basically they result from translation of the website from one language into another, and differences in the length of the strings of the language can result in layout failures because the text may become longer or shorter, and the elements that are around the text that's been translated doesn't adapt accordingly, leading to elements that are overlapping one another or appearing in positions that they shouldn't be appearing in. So aesthetics are very important for websites because aesthetics affect perceived usability by users, also accessibility, and also the credibility of the website and the product that it's offering. Studies been found to show that it engenders user loyalty, and also that the presentation failures can basically lead to lost revenue. So although some of these layout issues don't necessarily harm the functionality of the web page, they can lead to serious effects like the company losing business. Cross-browser issues are a particular concern because there are so many different devices in use these days and different browsers for rendering the content. So if you if you put XBI as a search term into Stack Overflow, there's a large number of posts that are returned that are detailing different issues that have been uncovered from different browsers and ways of fixing them and strategies for fixing them. In a study done by Chowdhury et al., it was found that XBIs are present in 57% of the websites that they looked at. And these were just all down to the same problem that there are different interpretations of the HTML CSS standard by these different browsers that lead to these different layout problems. So we're using the AVM in this approach to fix these cross-browser issues. The goal is basically to adjust the CSS of the web page that positions the HTML elements, and to use the AVM on the different parameters to move the elements back into the positions that they should be for the browser that's exhibiting the XBIs. So the CSS to the web page will look something like this. You might have a particular CSS declaration relating to a HTML element. It's being positioned on the left of the browser by 20 pixels, the margin for that particular box by 4 pixels. And if it's out of position for one particular browser rendering, we can use the AVM to basically operate on these parameters, and with a fitness function that quantifies how close the rendering of the faulty version of the page is to the correctly rendered version of the page. We can find what the difference in the location of elements is and the difference in the size of elements, and use that as a fitness function to manipulate the CSS values into something such that the website now renders correctly in the browser that originally had the XBI. So suppose we have an XBI in our website. I've rendered these two boxes on top of each other, so they've been two different browsers, but here I've rendered them on top of each other in one browser just to make the point. But the blue box is correctly laid out in our web page, but the red box is out of position because of the way that the browser that it's rendered in has interpreted the HTML standard, the CSS standard. And for this particular box, it's positioned 20 pixels from the left of its container, which is invisible here, and 20 pixels from the top. And our technique, using the AVM, will start to search on those two values and start to nudge those values into positions so that the box is now rendered into the correct position. So we're searching for new CSS values, and local search is basically ideal for this problem because the buggy version of the website is not so far away from the way that the website should be rendered that small changes aren't completely the wrong thing to do in trying to find a fix.
How did you manage to get the Luxembourg flag on your slide?
Well, I knew where I was going on to be patriotic, you know. completely intentional. So our solution consists of 5 different stages. The first step is to identify these XPIs, and we use an existing tool called Expert to do this. So we have our page under test as input to this approach, a reference browser and a test browser. So the reference browser has the correct rendering of the web page, the test browser has the incorrect rendering, and we push this to our approach, and the technique starts by identifying the XPIs that are present in the page. It then extracts these things called root causes, which are pairings of CSS properties with labels that help localize the CSS properties in the CSS that potentially are at fault. We then use the AVM to search for candidate fixes for each of the individual root causes, and then there's a final stage, a search stage, that then tries to combine all of these candidate fixes together to produce a repaired page.
I have a quick question.
Yep.
I forget. If you have differences across browsers, but the rendering is correct on one and incorrect on the others,
Yeah.
in what you're trying to make them consistent.
Yes, across both browsers.
But if you don't know which one is correct or which aspect is correct or which one, by making them consistent, isn't there a chance that you will produce an incorrect rendering on all of them?
Yeah, no, yeah.
You see what I mean?
Yeah. So the assumption is you know which one is correctly rendered, the reference browser. So in this scenario, the developer will develop the website for one particular browser, and they'll see that it's all looking correct. So they'll know that that's the correct rendering. It's when they then go and try to test the web page in other browsers. Yeah. When they then view it in another browser, they'll see that it's all moved around and that it needs to be moved back into position again. So we obtain the initial XPI set using this tool called Expert. So it'll identify the HTML elements that are concerned, and it will pull out the XPaths for those from the DOM. And it'll also produce a little text label to say what the particular issue was, what a summary kind of label saying what the differences were. And here it's basically pulling out the fact that the two elements E1 and E2 have a difference in terms of their alignment to the top of their container. So it pulls out this label and it pulls out the two elements that are different across the two browsers. From this, we try to extract a series of root causes. So these are the HTML elements coupled with the CSS property and the CSS value. And we identify the properties based on the label, so that we know that when two elements are incorrectly aligned to the top of their container, there are only certain CSS properties that could result in that happening. So here we've pulled out the margin top and the top CSS property because those are two key CSS properties that could be potentially related with this particular failure. We pull out the values from the CSS for those particular HTML elements and those CSS properties, and then these become the basis of the AVM vector that we then operate on in order to find these adjusted values. So we have the original root causes. We throw the AVM at this to adjust the values such that the different HTML elements are laid back into the correct positions, and we have those values, those corrected values generated from the AVM search using this fitness function that checks when everything is properly realigned. Then following this, we have a series of these candidate fixes. We basically then use a random search to select the ones to produce a final patch. So we did use a genetic algorithm with this originally, but found that the problem was simple enough that you could throw a random search at it, and that would be suitable enough to pull out these different candidate fixes and then combine them all together to produce an overall fix that will minimize the number of XPIs in the web page. So there's this final step of just checking whether we should terminate or not, whether all the XPIs are resolved. If they're not, we do other checks like making sure that we're not making the problem worse, that the solution is going in the wrong direction, and if so, we terminate under those conditions as well. If the solutions are making progress towards resolving the number of XPIs, then we'll loop back and continue the process and go around the loop another time. But what this technique will eventually produce is a series of these candidate fixes, that look like these. They're these particular vectors. We then need to map that back into a CSS declaration. And in order to do that, we generate this new section of CSS that's targeted towards the particular browser, such that the browser concerned that has this XBI will be the only browser that will actually use this additional piece of code. So we're careful to wrap it in a particular CSS declaration that will only be interpreted by the browser of the XBI, otherwise we'll be unfixing, if you like, the correct version of the web page as well. So that wouldn't be good, because then we'd be introducing XBIs into the original version of the page that we don't want. And then we generate a CSS selector based on the XPath, and we output the correct CSS property. So in our results, with this particular tool and using Expert to tell us how many XBIs are in the original web pages and fixed web pages, we're able to find that we're able to reduce the number of XBIs by a median of 93% and a mean of 86%. But basically, with the human study that we did, we found that actually we'd been able to fix all the XBIs, because the other ones that were identified by the Expert tool were down to pixel level differences that weren't actually perceptible by the human. Our tool's pretty fast as well, so for certain sites. For others it takes a bit longer. But I mean, fixing XBIs is a hard problem in practice, because you're trying to balance CSS across two different browsers. You have to understand the CSS code and its structure, how it links to HTML. So to do this manually is a challenging task, so any automation, even if it does take a long time, is likely to be of use to developers. We have this tool, Xfix, which is available on GitHub, and these two supporting papers that were at ISTA this year, so this tool's available for you to try out. And just as a summary of everything that I've talked about, so basically the thread through this talk has been the AVM technique, a powerful search technique, how it's been used for testing programs, and this more recent work on testing database schemas, and of late fixing website layouts as well. So that's it. Thanks very much.
We are in a bit late, later than expected. One comment or question? No? This guy.
Yeah, actually, are you really claiming that the AVM, you know the new no free lunch theorems, right? So I mean, why would it be better than hill climbing? I don't see.
Well, AVM is a form of hill climbing.
Sorry?
AVM is a form of hill climbing.
Yeah, exactly. So I mean, why is it important to? Isn't it kind of orthogonal? The problems we apply searching to specifics.
Well, I mean, the no free lunch applies. I guess what this work is showing is that the problems have certain landscapes which the AVM can exploit because of this acceleration mechanism it has through the pattern moves. So yeah, sure, if you were to apply the AVM on every single fitness landscape, then there'd be no net difference, right? But for these particular problems, the sensitivity analysis allows it to identify which are the kind of principal variables that need to be adjusted. And then the pattern moves allow for this acceleration.
As long as there are not high-level interactions.
Yes, yeah, that's when the whole thing doesn't work and you need a GA.
Yeah, this is mine.
Okay.